Okay, hi everyone, and welcome to Chapter 7, Nuclear Process. I'm going to be covering what I consider the main points of Chapter 7 and hopefully a brief and informative discussion. So I'd like to focus on three areas, three main decay process. There's other ones listed in your textbook, but we're going to talk about alpha decay, beta decay. Beta is positive and negative, two different types. We're talking about binding energy and mass defect, and that relates to how much energy we get out of, let's say, nuclear fission, which is what powers our reactors. And then we're going to be talking about all these different units, the electron volt, the joule, the kilogram, the atomic mass unit, and how they all connect through Einstein's famous equation, E equals mc squared. Okay, let's start with the decay processes that I'm interested in. Alpha decay is when a parent nucleus unstable, so it spits off an alpha particle. An alpha particle is really just a helium nucleus. So why do we call it an alpha particle? At the time when they were doing research into this, like, at the beginning, Marie Curie and all those guys, they didn't know what was coming out. So they just called it a, alpha particle. So here, just some notation, right? This is the atomic number, which is the number of protons in the nucleus. This is the mass number, and that's the number of protons plus neutrons, the number of nucleons, you could say. So if a helium nucleus pops out, helium has 2 protons, 4 neutrons. That must mean the resulting daughter nucleus has 2 less protons and 4 less nucleons. So altogether it weighs 4 less, and it's a new atom altogether. This is called a transmutation. That's the first one. Next one is the beta negative type of decay. So you have a nucleus decaying into a new nucleus, and what gets emitted is an electron and an antineutrino. So where did this electron come from? Well, it looks like we have one extra proton here, but the same mass. So you can think of this as a neutron disintegrating into a proton and an electron. This is not exactly like that simple, but it's okay. You can see the total charge here is 0, and the total charge here is also 0. We have positive and negative, so we haven't disobeyed the law of conservation of charge. So if you get a neutron from here disintegrating into an electron and a proton, this number would go up by 1, but this number would stay the same. The textbook doesn't mention the antineutrino. It's not a big deal, but it is also part of the process. Beta positive is nearly the same thing, but instead of an electron popping out, what comes out is a positive electron. Yeah, positive electron, we just call it a positron instead. Same mass, but opposite charge. It's the antiparticle to the electron. And I guess also of note here is instead of a neutrino, an antineutrino pops out. So let's take a look at what this equation looks like down here. So what happens is a proton disintegrates. So if a proton disintegrates into a neutron and an electron, and a positron. So the charge here is positive, neutron is 0 charge, and positron is positive. So we have obey the law of conservation of charge too. It's just a way I like to think of remembering these two processes, as this one being a neutron disintegrates, and this one a proton does. So if a proton disappears, its proton number goes down by 1, but remember the mass number doesn't change because that proton became a neutron and has the same mass. Those are the 3 types of nuclear decay that I'd like to focus on. Okay, next topic, what is mass defect and binding energy, or I think maybe more clearly stated, separation energy. You may be familiar with the atomic mass unit. It's defined as 1/12 of the mass of the carbon-12 nucleus. So we're going to use this number here. So the proton, down to 1, 2, 3, 4, 5, 6, 7 significant figures, has a mass of 1.672614 times 10 to the negative 27. The neutron is almost the same. So in grade 9 and 10, we just say that they are the same, but actually these significant figures are going to come into play soon. Here's the mass of the electron, and they are converted to mass units here. And of note is we're also going to be using the electron volt and the joule as units for mass soon. If you're wondering how we can use joules for mass, remember, they are interchangeable via this. And if you don't know what the electron volt is, we're going to have a whole section on that. So let's discuss this. How much does an oxygen atom weigh? And when I say that, I mean, like, what's its mass, right? So if you think about the atom with this picture in your mind, and then you think about all of its components, you know, logically they should be the same mass. So let's just try that calculation, right? So if we mass the components, we're going to get 8 protons plus 8 neutrons plus 8 electrons, right? So just factoring out the 8, it's a proton plus a neutron plus an electron. And if I just zip up to this table here, it's 1.672614 times 10 to the negative 27 plus the neutron, 1.67492 times 10 to the negative 27 plus the electron, which is 9.10956 times 10 to the negative 31, all in kilograms and all multiplied by 8. That will give me the mass of the components. So that calculation gives me 2.67876 times 10 to the negative 27 kilograms. Let's convert that to atomic mass units by dividing by 1.66 times 10 to the negative 27. That's number of kilograms per atomic mass unit. And you get 16.1371. Units. Okay, let's bring up the periodic table here and take a look at oxygen. Here's oxygen here. The mass stated here is 15.999. So we'll go back here. There's a pretty big discrepancy between the atomic mass of oxygen. The mass is 15.999 units according to the periodic table. That's the mass of the atom, compared to the value we got versus the mass of the components. Okay, so what does this mean? We have what's called a mass defect here. So mass defect is the mass of the components. In this case, the mass of the components was 16.1371 minus the mass of the atom, as looked up on the periodic table, 15.999. 0.138 units. That's what we'd say is delta M, the mass defect. This is delta M here. So what does it mean? It means that if you take up a whole bunch of protons and neutrons and you put them together, they form an atom which is more stable than their components separately, and they release energy, and so they drop in mass. That's an interesting concept. So summarizing it kind of like this: mass defect is positive if your isotope is stable. Mass defect is negative that's when a more stable option would be to just fly apart. They have less energy if they're apart from each other. Interesting. Okay, related is the binding energy. It's just the mass defect converted to energy via E equals mc squared. So you could take this and you could plug it into E equals mc squared, but what would your energy be in? Would it be in joules? We'll come back to that one. Sometimes called separation energy, binding energy. How much energy would it take to separate the atom into its components? Another way of thinking about it is how much energy is released when those components come together. So the only reason matter exists in the form it does is because it's in a lower energy state than it would be otherwise. If it was more stable to be separated into protons and neutrons, well, the universe wouldn't exist as you know it, because atoms would not form. Okay, let's talk about some of the units you might see coming up here. We have the electron volt, the joule, the kilogram, and the U. The only one you're not familiar with is the electron volt. So you remember what a volt is? Maybe you don't. Volts are joules per coulomb, right? So energy divided by charge. That's from grade 9, I think. So this is joules. This is, that's volts. This is joules, and this is coulombs. So you could say that 1 electron volt is the energy required to raise the potential, to raise the electric potential, to raise the voltage of 1 electron by 1 volt. Yeah, that's so obviously clear, right? But maybe the equations will be clear. So you have 1 volt. What's the energy required to raise 1 electron? The charge on an electron is 1.6 times 10 to the negative 19 coulombs. So if you rearrange this, you can see that the energy required would just be 1.6 times 10 to the negative 19 joules. And instead of using that number, we just call that the electron volt. Oh, that looks like a division symbol. Let's say that. Let's just do this. 1 electron volt is defined as the energy required to raise 1 electron up by 1 volt. If that doesn't make any sense, just say it to yourself 3 times fast, and it'll still not make any sense. So now we have a conversion between electron volts and that's not bad. Electron volts and joules. We know the conversion between kilograms and atomic mass units. 1 U, sometimes I write AMU, same idea. Seen sometimes also Daltons being used on the web. It's kind of interesting. So using these two, we can now safely convert between all of these. Power. Okay, so using these conversions, let's try and calculate the binding energy for oxygen. I'm going to need the mass of this oxygen, the mass defect. Oh, that's not what I'm looking for. Sorry, the mass defect was here. I'll put that there. So that's the mass defect as calculated from before, and we can use E equals mc squared to calculate this. But if you want joules to pop out, then we have to put in kilograms. So to convert 0.138 units into kilograms, just multiply 166 10 to the negative 27 kilograms per unit, and we will get our mass in kilograms. 2.2908 times 10 to the negative 27 kilograms. Pop it into here. 2.2908 times 10 to the negative 27. C is the speed of light, 3.0 times 10 to the 8 meters per second. All of this is squared, kilograms, for a total binding energy of 2.06172 times 10 to the negative 11 joules. It's a really small number. That's why we have the electron volt. So let's convert it to electron volts. So in EV, we put in 2.06172 times 10 to the negative 11 joules, multiplied by the conversion factor. 1 electron volt has 1.6 times 10 to the negative 19 joules. Joules cancel out, and we're left with electron volts. It's 128,857,500 electron volts, which is really, really huge. So let's just go kilo electron volts, mega electron volts. So we'll say 129 millions or mega electron volts. Much more convenient unit to use in this case for the binding energy. Let's try one more problem that is in your textbook, more or less. It says calculate the energy released when uranium-236 undergoes alpha decay. So a couple things. The notation, this tells you the mass number. So we're talking about uranium-236, and it has 92 protons. It undergoes alpha decay, which means it's going to spit out a alpha particle, which you can symbolize with He24. You can also use the alpha symbol if you like. And that means if there's two protons here for the alpha particle, that means we've only got 90 left over. Remember, we also have lost 4 total nucleons, 2 protons, 2 neutrons. So we're down to 2, 3, 2 for this one. If you look this one up, this one is thorium. You get this one. So we need to, we're also missing some electrons here. What happens to the electrons during a alpha decay process is like they just go shooting off. So you can think about adding the 2 electrons if you want to here. You can instead think about this as the whole helium atom and then look that one up. That's what I'm going to choose to do in this case. However you do it, it's fine. The idea is like you're thinking about what's the mass of uranium-236? What's the mass of thorium-232? And what's the mass of this helium atom here? And we're going to put them on the scale, right? Just like before. And which way does the scale tip? If energy is being released, then this side has got to be heavier than this side. So let's check out these values. I'm just going to pop open one of these windows. Mass of uranium-236, and we're getting 2360. Just copy that into here. All this extra stuff, perfect. Mass of thorium-232. Oops. And there it is. And the mass of a helium nucleus. Yeah, let's just say of helium-4. We'll just take the whole atom. So what we're doing is we're comparing this number plus this number to this one. And if we want energy to be released, this has got to be greater than that. Performing that calculation, the addition gives us 236.040652 compared to this 236. So they're almost the same. To 5 sig figs, they're the same, but they're not. So let's calculate the mass defect here. It's just 2360. I want, the magnitude, because I know energy is going to be released here. 5568 subtracted by 236040652. I get a mass defect of 4.916 times 10 to the negative 3 atomic mass units. Okay, so now we got to convert to kilograms and then use E equals mc squared, which is a lot of painful conversions. How about we just try and find the amount of electron volts per atomic mass unit? How many electron volts are there per atomic mass unit? So we'll use E equals mc squared, and we'll put in 1 atomic mass unit. And this will give us the energy of 1 atomic mass unit in joules. That number is 1.494 times 10 to the negative 10. And then if we want to convert that energy into electron volts, we know that every electron volt is 1.6 times 10 to the negative 19 joules. Which is 933,750,000 electron volts. So let's simplify it to 934 billions of millions of electron volts, excuse me. That's 1 unit. So, considering we don't have that many units, we only have this many, we should just convert our number by saying 4.916 times 10 to the negative 3 units multiplied by 934 mega electron volts per unit, and that will give us 4.59 million electron volts. In case you forgot what the question was when uranium decomposes via this process of alpha decay, how much energy is released? We got 4.59 million electron volts. And that concludes our brief tour of nuclear power.